Hi everyone, and welcome back to this series of solving practice problems about different topics in numerical method. And this time we'll talk about or solving questions about roots of nonlinear equations. So the first question is using the bisection method. We want to find one root of this function, and the root is, we are told that it is between 0 and 1, and then we need to stop after 4 iterations. So first of all, let's make sure that our root does exist between 0 and 1. So let me find f of 0, which is equal to basically 1, and f of 1 will equal to 1 cubed minus 3 1 squared plus 1, and this will give me minus 1. So then f of 0 times f of 1 is less than 0. So indeed, there is a solution between 0 and 1. Now, we'll start our iterations. So our first iteration here. So this is our first solution. We will start with x, 1. We'll take the average, which is 0 plus 1 divided by 2, which is equal to 0.5. Now, your answer is either between 0 to 0.5 or 0.5 to 1. So we need to find f of 0.5, which is equal to 0.375. So it's a positive value. So indeed, f of 0.5 times f of 1 is basically less than 0. And hence, now the answer, your new answer now will be between 0.5 and 1. So now let's go for the second iteration. And again, now we will take the average value between the two new intervals. So my x of the second iteration will equal to 0.5 plus 1 divided by 2, which will give me 0.75. Again, I want to find f of 0.75, and this equal to minus 0.2656. Okay, so it's a negative value. So basically, indeed, now we are sure that your interval will be between 0.5 and 0.75, because f of 0.5 is a positive value, f of 0.7 is a negative value, so the multiplication of f of 0.5 and f of 0.75 is a negative value. So now this will take us to the third iteration. So x of 3 will equal to 0.5 plus 0.75 divided by 2, and this will give me 0.6225. Now I need to find f of 0.625, and this value is equal to 0.0723. So f of 0.625, which is a positive value, times f of 0.75, which is a negative value, it will be less than 0. So the new interval now is between 0.625 and 0.75. Finally, our fourth iteration will take the average, 0.625 plus 0.75 divided by 2, and this will give me a value of 0.6875, and I will stop here. I don't need to go and find the other interval because we are looking for 4 iterations only, and this is the end of the 4 iterations. Okay. Here in this question, again, we will be using the bisection method, but here we are given a different stopping criteria. We want to stop when basically the fault is, or the error is less than 5%. So now we have to calculate something else, and basically here the error will be the approximate absolute relative error. When we say the error, that is what is meant in that context. So it is the approximate relative absolute error percentage-wise, okay, because it's given to you in 5%. So this is our function here, and we are giving that the answer is basically between 0 and 4. So f of 0 is actually substitute there, so it will be equal to -2. F of 4, the other side of the interval, is basically equal to 0.185. So f of 0 times f of 4 is indeed less than 1. And hence, basically, we will have at least one. There's an odd number of solutions. So assume there is one solution between these two functions. So we'll start the iteration. So we'll have iteration number 1. So basically x of 1 will take the average of 0 plus 4 divided by 2, which is equal to 2. And so this is your first iteration. This is your first solution. So now f of 2 will be basically equal to minus 0.71. It's a negative value. So now we know that f of 2 times f of 4 is less than 1. And hence the new interval now is between 2 and 4. Now we go to iteration number 2. Now in iteration number 2, take the average value of this. So x of 2 now is equal to 2 plus 4 divided by 2, which is basically equal to 3. So the first answer was 2. The second answer was basically 3. Now the approximate error percentage-wise is equal to the current, the existing, and of course, the absolute value, solution 3 minus the previous one divided by 3 times 100, which is equal to 33.3%, still way higher than the required criteria. Okay, now we need to find f of 3, which is basically equal to minus 0.269, and hence now the new interval will be between 3 and 4, because the value at 4 is positive, at 3 is negative, so it has to be between these two. Now we'll go to iteration number 3. Iteration number 3. So x3, take the average, 3 plus 4 divided by 2, which is equal to 3.5. Take the percentage of the error, current solution minus the previous one divided by the current solution times 100, which give me 14.3%. Okay, so still we are higher than the required, so we need to go to the next step. You find f of 3.5, and this is equal to minus 0.05. So still the solution between 3.5 to 4. Okay, so now we need to move to the fourth iteration, x4, which is equal to 3.5 plus 4 divided by 2, which give me 3.75. Let me calculate the error, which is equal to 3.75 minus the previous solution, 3.5 divided by 3.75 times 100, and this will give me 6.67%, still higher. So we need to find the value at f of 3.75, which is equal to 0.06. Hence, the new solution is between 3.5 and 3.75, because their multiplication is basically less than 0. So this is the new interval. We'll go now to the next fifth iteration. So the fifth iteration on the solution here, x5 will equal to 3.5 plus 75 divided by 2, and this will give me 3.625. Then you find the error, which is 3.625 minus 3.75 divided by 3.625, and this will give me 3.45%, less than the 5%. So I will stop here. I don't need to investigate anymore, and this solution will basically satisfy my requirement. Now, the third question is basically about using the fixed point iteration. And you are given the function here. We want to find the root, one of the roots here. And we start with an initial guess x is equal to 1, and when I stop after 4 iterations. Now, as you know, that how to solve this question, we have to rewrite the equation in the form of x equal to g of x. That is what you need. You need to have x in one side and then the rest. And here you are giving two different g of x's. 0.4 plus x minus 0.1 x squared. So this is basically adding x to both sides. And the other one solving for x from the same equation. So we want to see the convergence of each one. So let's start with A. So your x of the first iteration is basically equal to 0.4 plus 1, because this is our initial guess, minus 0.1 times 1 squared, and this will give me a value of equal to 1.3. Then x of 2, the second iteration, is equal to 0.4 plus 1.3 minus 0.1, 1.3 squared, and this gives me 1.531. X at the third iteration equal to same, keep on updating the value each time, plus the new value 1.531 minus 0.1 times 1.531 squared, and this will give me 1.696. So it's clearly, it is converging. Slow convergence, yes, but it is basically converging, equal to 0.4 plus 1.696 minus 0.1, 1.696 squared, and this gives me 1.8087. So the error keep on decreasing. Okay, so that is the conversion of the using the first g of x. Now let's go to part B, and now your g of x, this is part B, your g of x now is equal to 4 over x. Let's try to substitute x0 as we know it is equal to 1. So basically your x1 will equal to 4 over 1 equal to 4. X of 2 equal to 4 over 4, which is x here, is equal to 1. x3 will equal to 4 over 1 equal to 4. x4 is equal to 4 over 4 equal to 1. As you can figure out here, it's oscillating. It's not really converging. And basically, we can tell if the function is basically will be converging or not converging by basically calculating the derivative of g of x. Okay, absolute value of that. So when you do this for the first one, it is 1 minus 0.2 x. So when you substitute at x equal to 1, this equal to 0.8 less than 1. So basically it converges. Okay, now when you go for g1 or g2 actually, or the other g prime of x, basically here it is 4 over x. So x squared minus 4, take the absolute value, substitute, this will give you 4 greater than 1. So it will not converge. Now let's see the last question here. So here we have a fourth order polynomial, and we starting from x equal to 0 using Newton-Raphson method. We want to find one of the roots. Stop the calculation when the absolute relative approximate error is basically less than 0.1%. Okay, so that is the criteria. Now, the general formula for Newton-Raphson that x at iteration I plus 1 equal to xi minus f of x of I divided by the derivative of x of I. Okay, now we know f of x basically is given to us as equal to x4 minus 21x cubed plus 147x squared minus 379x plus 252. So from this, I can find f prime of x, which is equal to 4x cubed minus 63x squared plus 294x minus 379. Okay, so that's basically your f of prime of x. Now we start the iterations. Okay, so we start with x1 equal to the previous iteration, the previous number is basically 0 minus f at 1 divided by f prime at 1. When you substitute the value, I will use 4 significant digit by approximation. You will get 0.6649. Then we'll go for the second iteration. Okay, and this is equal to basically 0.6649 minus f of 0.6649 divided by the derivative of the function at 0.6649. And if you do that, you will find that basically the answer is equal to 0.9457. So let's calculate the error here between these two consecutive iterations. So basically your error, approximate error, is equal to the current basically solution minus the previous one, 0.6649 divided by 0.9457, all absolute value, all times 100, and this will give me 29.7%. Still very high error. Now, because this is the first error we calculate, now let's go for the coming basically iteration. So we'll go to x of 3 would equal to 0.9457 minus f of 0.9457 divided by the derivative of the function at 0.9457. And you do that, you will find this is equal to 0.9982. Now, compared to the previous answer, it was 0.9457. Clearly, now we are converging. Now, let me calculate the approximate relative error. It is 0.9982 minus the previous iteration, which is 0.9457 divided by 0.9982. And this will give me 5.26%. So the error dropped drastically from 29.7 to 5.26%. And then we want to find x4, which is equal to basically the 0.9982 minus f of 0.9982 divided by f prime of 0.9982. And this will give me approximately one solution of 1. It was 0.9999998, so we can say it's approximately equal to 1. And basically the EA is equal to this 1 minus the 0.9982 divided by 0.998, divided by 1 times 100. And this gives me 0.17%, still higher than the 0.1%. But now when we go to x5, you will find the answer is equal to 1 minus f of 1 divided by f prime of 1. And this is equal to 1. So now the answer, so the error is almost equal to 0. And that is basically the stopping criteria of the Newton-Raphson question.